Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 3.9.3 and 9.4, logarithms and their properties. Video 1, review of exponent rules. Now, some of these exponent rules were reviewed when we were doing the previous homework, section 9.1 and 9.2, about inverse functions and exponential functions, but a couple of these exponent rules might be new, but let's summarize them pretty briefly. All right, exponent rule number 1. Well, they're not in any particular order, so I'm just going to write them in the order that they come to mind. One exponent rule is that if you take any base, we'll call it b, and raise it to a power, we'll say the xth power, and multiply it times the same base, we'll say b, but to possibly a different power, we'll call it y, then you can keep the base, b, and add your powers. This is what's sometimes called the additive law for exponents. But in words, what this rule is saying is this. Let's move my picture up here and widen this. This says if you multiply two exponential expressions with these same bases, let me go fix that if there, and we'll move this text box over just a little bit. If you multiply two exponential expressions with the same bases, then you can add the exponents, but keep the same base. For example, if we wanted to do something like, we'll say w to the third power times w to the fourth power, all this says is that you add them to get 7, and then you keep the w the same. Now, the inclination here is to want to multiply the exponents because it says times. But if you were to write out what w to the third power means, w times w times w, and then w to the fourth power, and then bring down the multiplication that joins them together, it's pretty obvious that the exponent is just counting how many times we multiply the w's. So if we multiply it 3 times and then 4 more times, it's a total of 7 times. So that's all that rule says. If you multiply two exponential expressions with the same bases, then you can add the exponents, but keep the same base. And then for rule number 2, let's do the one that says when it's time to subtract. And the time to subtract is when you divide two exponential expressions with the same base, but possibly different exponents. So we'll say b to the x divided by b to the y. And remember, a fraction is just a division problem. Keep the same base, subtract the exponents. And again, this can be written as words. To divide two exponential expressions with these same bases. I think same base should be singular there, so I'm going to go back up here and fix it as well. All right, so back down here. To divide two exponential expressions with the same base, well, let's try that again. If you divide two exponential expressions with the same base, then you can subtract the exponents, but keep the same base. I don't really have room to do a red example here, except I do if I just show you up here. Let's put it in red. Sorry, there's a little hair on my screen or something. For example, if you had something like w to the 6th power divided by w to the 2nd power, and I don't know why I'm using w again, you would just subtract the exponents. It's always top minus bottom. 6 minus 2 is 4. Even if the top number is smaller, it's always top minus bottom. And this works because if you were to write out the 6 w's on top and the 4 w's on bottom, the rules, the 2 w's on the bottom, excuse me, the rules for canceling in a fraction is you can cancel parts of multiplication problems, and all these w's are parts of multiplication problems. 6 w's cross out 2 of them, leaves 4. So that's the reason that rule works. All right, let's draw a line separating these just because it's going to get kind of congested. If I don't, I may have to move something down. All right, there we go. Okay, so what would be a good third exponent rule? Well, how about a rule that tells you when to multiply? goes something like this. Let's say you have any base, we'll call it b, raised to any power, we'll call the exponent x, but then you raise that entire expression to another power, we'll say y. Then you can keep the base, but multiply the exponents. So let's see if we can put this in words. It's always good to try to describe these to make them more, so they make more sense. Try describing them in your own words. If you raise a base to a power, then raise that result to another power, then you can just multiply the powers into a single power. Okay, am I using power? Sometimes I use exponent, sometimes I use power. But they're sort of synonymous. There's a very subtle difference between the two, but we're not going to sweat the difference. For example, let's say that we did something like b to the 4th power and then raised to the 2nd power. Well, this just says we can multiply the 4 and 2 and make it an 8. And the reason it works is if you were to write what it means to square this, to square something means to write it 2 times. But we have a rule that says we can just add our exponents, but to add something to itself just means to multiply it times 2, or whatever the particular numbers would be. So it's a direct consequence of rule number 1. You could also write out all the b's, count them, and say, hey, I have 2 groups of 4 b's for a total of 8 b's. All right, let's go ahead and put a line under that so we don't run into it with the next rule. Now, if we had a rule that tells you when to add, when to subtract, when to multiply exponents, it would make sense that there should be a rule that tells you when to divide exponents. And there is, but it uses radicals. If you have a root, and we'll call it I'm going to call it the wife root. Normally there'd be an in there, but I'm trying to be consistent with my use of the x and the y. And inside the radical sign, you have b to the x power. Then all you have to do is divide the power by what's called the index of the radical. I don't know if I have room to write that in there, but the number that sits here is called an index. And so and I'll show you a numerical example here in just a second to really emphasize what it means to be a root. But in words, it would go something like this. If you take a root of a power, then you can divide the power by the index of the radical, but keep the same base. And again, this is much easier to do than it is to put into words. For example, if we had something, and I'll use a numerical example here in just a second. If we had something like the cube root of, we'll say, 2 to the 12th power, you don't have to figure out 2 to the 12th power. All you have to do is divide 12 by 3 in the exponent, and that would give you 2 to the 4th power. Now, of course, being numbers, we could figure out what 2 to the 4th power is. 2 to the 4th power is 16. In other words, the answer to this is 16. And we could even figure out the answer to 2 to the 12th power. 2 to the 12th power is 4,096. But I just want to show you real quick, or rather remind you, hopefully, what it means if I said something like the cube root of 4,096, which is the answer to 2 to the 12th power, is 16, which is 2 to the 4th power. When you check a square root, you square the answer. When you check a cube root, you cube the answer. Whatever number the index is the answer that you use to, the power that you use to check your answer. So you would say that the cube root of 4,096 is 16 because 16 to the 3rd power is 4,096. In fact, I want to put this in a cloud just as a numerical example of what it means to take a cube root. Because we get so used to using just square roots, we don't see the other radicals too terribly often, like fourth roots, fifth roots, sixth roots, and so on. But we do run across cube roots. I just want to remind you what it means to be a cube root of a number. Your answer is the number you would raise back to that power to get back the radicand that you started with. All right. Other exponent rules that we're going to run across. We've seen some of these in the previous series of videos. If you take any base and raise it to the 0 power, you get 1 as long as that base is not equal to 0. And this one's easy to put in words. In words, all this says is any non-zero base raised to the 0 power equals 1. I'm missing some letters here. Any non-zero base raised to the 0 power is equal to 1. So for example, whether it's a number or a letter is irrelevant. If I said something like 5 to the 0 power, that would just be equal to 1. The only exception is 0 to the 0 power. We will not run across that. It is a calculus issue though, so we won't worry about it right now. In calculus, it's called indeterminate because we arrive at it, and how we arrive at it determines its value, but let's not worry about that right now. Okay, exponent rule number 6. We have also seen this one in the previous series of videos. If we take any base and raise it to a negative power, we'll say to the negative x power, that is equal to 1 over the base to the positive power. This also requires that the base is not equal to 0 because it would make the denominator equal to 0, and that would be undefined. So in words, we would say something like this. Any non-zero base, raised to a negative power equals the reciprocal, so 1 over, of the same base raised to the corresponding positive power. So for example, if we had something like 3 to the negative 4 power, that would be the same thing as 1 over 3 to the positive 4 power, which equals 1 over 81. But my point isn't what 3 to the 4th power equals. That's just a calculator problem. My point is what negative exponents do. All right, I think there's only a couple more, but if I think of another, I'll be sure to throw it in. The other two are, we're on number 7, are kind of distributive properties. Goes something like this. Let's say you have a multiplication problem. We'll call it A times B, and you raise that product to a power. Then you can essentially distribute the power. And I'm going to go ahead and put rule number 8, which is the same rule except for division, meaning if you divide two numbers, so they look like a fraction, and raise the result to a power, we'll call the power x, you can distribute the power across that division sign. In fact, I want to grab all of the second one that I wrote and move it over to the side here. I'll turn my video off so that I don't block the rule. But both of these pretty much say the same thing. In words, what both of them say is this. If you raise a product or quotient to a power, so a multiplication problem or a division problem to a power, then you can distribute the power to each part of the multiplication or division problem. So it's a distributive property type thing. So a couple of real quick examples. If I had something like 5w to the 3rd power, I could distribute the 3 across the multiplication problem, call it 5 to the 3rd power and w to the 3rd power. 5 to the 3rd power times w to the 3rd power. But the general consensus here, and I really want my face on the screen, I'll just put it somewhere that's not blocking the rule. The general consensus with powers and numbers is if you see a numerical exponential expression like 5 to the third power, you should follow through and figure out what it equals. 5 times 5 times 5 ends up being 125 W to the third power. Or if we had something like, and we'll just stay strictly numerical on this one, if we had something like 3/4 squared, let me make that 2 a little bit smaller. The rule number 8 says you can distribute the power to both halves of the division problem. Put 3 squared over 4 squared, both of them being numerical expressions, can be evaluated to 9 over 16. So that's all number 7 and number 8 is saying. And I think we've covered the main exponential rules, but there is one rule that I need to put that's almost like an anti-rule, meaning something that you can't do. And it's a follow-up to number 7 and number 8, which are kind of distributive in nature. Here's a critical rule that I see people in the highest level math classes make a mistake on because they're not paying attention. So we'll put it in a larger font size. Warning, rules 7 and 8. Let's widen this text box. Say you can distribute a power across a multiplication or division problem. And here comes the catch. And in fact, we'll put this in red because it ought to be. However, you can never distribute a power. Let's widen the text box. You can never distribute a power across an addition or subtraction problem. I see this all the time in upper level math classes. I mean, like calculus 1, calculus 2, calculus 3, linear algebra. I feel like I can get all this on one line. You can never distribute a power across addition or let's do this. Addition or subtraction problems. But I see this all the time. And, you know, at that level, I used to have more hair. I pulled it all out, yelling at calculus students. No, that's a joke. I did not yell at them, and that's not why my head looks like it does. It's hereditary. So if you're a young man watching this and your dad is follically challenged, got some bad news for you. But in other words, if you have something like x plus 5 to the third power, you cannot distribute the power. It is bad, 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 bad. So if you had something like, oh, let's say x minus 1 over 3 to the 5th power, what you could do is distribute it to both halves of the division problem. So to the top and to the bottom. What you could not do is distribute across the subtraction problem. So if you're going to be seeing exponents on top of addition, subtraction, multiplication, or division problems, it is critical that you know when you can and cannot distribute them. You can distribute across multiplication and division. You cannot distribute across addition or subtraction. There is a visual to remember this. If you know, please excuse my dear Aunt Sally, the order of operations. I know a lot of people, when they write PEMDAS, they actually write it like this. I do not like writing it like that. I prefer to write it like this. Hold on. I prefer to write it like this. And I look at it more like a totem pole. I put MD on the same line because they're the same level of importance as our AD, addition and subtraction. And then so I think of the order of operations as going down this list. Do your parentheses, do your exponents, do your multiplication and division left to right, your addition and subtraction left to right, left to right. But here's how this can be used to remember distributive properties. You can distribute multiplication and division across addition and subtraction. Gotta be a little careful when it's division and subtraction, but it is possible. You can distribute exponents across multiplication and division. You cannot skip a level. You cannot distribute exponents across addition and subtraction. That's too far down the totem pole. So that's just a trick for remembering when you can and cannot distribute. You can probably distribute one layer down. I say probably because there are some exceptions with division and subtraction. For example, if you had x plus y divided by 2, that can be distributed. Of course, you probably wouldn't write it like this. You would probably write it as x plus y over 2 and split into 2 fractions. So in that sense, you can distribute division from the right side of addition. However, it doesn't work the other way around. In other words, if you have 2 divided by an addition problem, you cannot distribute like that. And the reason is, if you add 2 over x plus y, you cannot split it into 2 over x plus 2 over y. That's not how you add fractions. So the distribution of division across addition or subtraction hinges on the rules for fractions. So sometimes you can and sometimes you can't. But one thing I could definitely say is that you can't skip a level in the order of operations. So do not distribute from exponents across addition and subtraction, because that skips the multiplication division level. You can only distribute across the operations immediately below you in the order of operations. I'm not going to save this as a slide on the PDF because it was just a discussion I wanted to have.